Dear students, today we will discuss the last chapter of the machine learning, which is called Naive Bayes algorithm, and it is chapter number 7 for you. So let's explore that what is in this chapter. Before going into the depth of this chapter, let me tell you that this approach, Naive Bayes approach, is basically probabilistic based approach, and probability will decide you whether that which direction the prediction will go, right? So mostly here we use not the normal probabilities, we use the conditional probabilities. That, for example, with respect to, for example, if there are two events A and B, so we choose that the combined probability with respect to sample A probability, that how it works, right? So it's like, it's not a straightforward like a probability, but it's kind of a complex probability, you can say. And this probability has also been used by a very famous scientist, Shannon, in one of the article which is published in 1945 approximately. And because of that one, we have this new technology, we have laptops, mobiles, and new technology. And that was like, which was used for information gain, entropy, like this kind of concept. So but here we are using it for prediction purposes. So we need to study about like a conditional probability. We need to know that what is the Bayes rule, what is the Naive Bayes algorithm, what are the assumptions for Naive Bayes, right? So basically Bayes rule was a mathematician or statisticians, you can say, and he turned this one into a classifier, and we need classifier for machine learning. So if the classifier is there, we can easily classify our data into labeling, and then we can see that what is our result. And moreover, this conditional probability is also used in fuzzy logic and advanced machine learning items as well. So Lutfi Zada here, he used the scientist. He also used this in a fuzzy logic, and initially people didn't believe on him that this can work in a different machines, like automated machines like robots, and automated machines like washing machine and dishwasher and all these things. So fuzzy logic was very like popular. So he didn't believe in binary logic like 0 and 1. They say there could be in between 0 and 1 as well. Why, let's try something like in between 0 and 1. So they say, why not 0 0.1? What about 0 0.2, 0 0.3 up till 0 0.9? So he said that if there is like answer is 0 0.9, 0 0.8, if it is greater than, he put some threshold value. We say that if it's greater than 0 0.5, we say yes. If it is less than 0 0.5, or then we say no, right? Or you can specify your threshold values, like maybe greater than 0 0.5, yes, 0 0.7, yes, or less than 0 0.7 means no. So it depends on your logic, that how you design your logic. So a probabilistic model of the observed data, and then prior knowledge. So prior knowledge is very much important. So the normal probability is basically the prior knowledge. For example, the probability of a dice is, for example, is 1 by 6. Probability of a coin is 1 by like 1 by 2. While the probability of the cards, I think the total cards are 53 approximately, I think, if I'm not wrong. So 1 by 53. So everything has this called the prior knowledge. They have the prior probabilities, and based on these probabilities, we find new probabilities, which is called conditional probabilities. So classification problem, yeah, training data, we have examples from this one. And then we have D are the data objects to classify, and H of D are the correct classes info for the D of this one. And goal are, like, for example, this one, new goal, and provide, for example, they have inputs, you have supervised learning. And by the way, this Naive Bayes algorithm is also supervised one, and because we know that what are the outputs over here. It is not like the cluster algorithms or KNN or unsupervised learning, where there is no proper algorithm or proper, like, labeling. uh, yeah, so info, training info, we have the desired output as well here, and error can also be the target output minus actual output, just like MAPA, like, or like MSE. The kind of errors are also like can be obtained from here. So a word about the Bayesian framework. It allows us to combine observed data and the prior knowledge, provides a practical learning algorithm as well. It's a generative model-based approach which offers a useful conceptual framework. This means that any kind of objects, for example, time series, trees, etc., can be classified based on the probabilistic model specifications. Yeah. So, conditional probability is defined as the likelihood of an event or like outcome which is occurring, like based on the occurrence of the previous events or something outcome. It's more calculated by multiplying the probabilities of the preceding events by the updated probabilities of the succeeding or conditional events, right? So you can see here in the formula, you can see, so we have some prior probabilities like P of A. For example, the probability of a coin is 1 by 2, probability of a dice is 1 by 6. So these are the prior probability. But if you see probability B slash A, this is like conditional probability, and it's called likelihood, the probability of B being true given A is true. So if A is true, then so what is the probability of B to be true? This complex relationship here. And probability of B is normal. Okay, so we marginalize this when we divide it. So this probability, we call it, it is marginalized probability of B being true. Like so, see here, so probability of B, probability of A, these are prior probabilities. We already know that one. Okay, and then we find posterior probabilities by this formula, and the posterior probability means that the probability of A being true given B is the true, right? So now see, this is all true. So we can say total tautology. Yeah, so here is all tautology. Everything should be true in this scenario. Yeah, so this is the same thing in different parameters. Okay, so just go through that one, and mathematically it has been shown here. So just if you want to let me read and see, yes, Thomas Bayes was a British mathematician, okay, from 1763, and he provided calculation for the probability of this some information. And based on that one, our new technology is based. Basically, we are trying to find probability of A given the B is true. And POP is called prior probabilities, which means it's the probability of even before the evidence. Yeah. And B slash A is called the posterior probability, probability of even after the evidence is seen. With regards to our data set, this formula is here. So this is very clear now. Okay, so POB is called the probability, prior probability. Yeah, as we already know, it's normal probability, which we already study in a school level. But P slash A might be this included in the college level nowadays. But at our time, it was not included in school level. So yes, at university level, you must be studying this one if you are learning engineering or computer sciences. So especially machine learning. So probabilities of even after the evidence is seen, with regard to our data set, this formula can be rewritten as like this one. So Bayes rule is a way to find P of y of x from P of x of y. So evidence, yeah, evidence slash outcome, knowing from the training data, and then outcome slash evidence to be predicted for the test set, right? So one is like in all evidence you already have it, and with the outcome. Another you want um, to be predicted on the right hand side. Yeah. So Bayes rule provided us with a formula that probability of y can sometimes feature x. In real world problem, we hardly find any case where there is only one feature. And when the feature are independent, we can extend Bayes rule to what is called Naïve Bayes, which assumes that features are independent. That means changing the value of one feature does not influence the value of other variables, and this is why we call algorithm naive, right? Yeah. So this is why the algorithm naive has been the word has been derived from it. So naive Bayes can be used for various things like face recognition. People are using weather prediction, medical diagnosis, new classification, sentimental analysis, a lot and more as well. Yeah. So just to summarize that why we call it naive. So because when the feature are independent and we can extend Bayes rule to, so that's called Naive Bayes, and we assume that feature are independent. That means changing the value of one feature does not influence the value of other variable, and that's we call naive, right? So I think things becomes more clearer now. This is more mathematics about this formula. So just like dig deep into this mathematical version, and you will find that and how this works. And this is like so just instead of like sometime if you have many instances, you can say, of x, just like we have xi, then instead of just like keep multiplying, it's better to apply this sign, which is looks like a pi sign, but it's not a pi, but it's like a this sign, like tells about the product basically. So here is like we have a predictor probabilities, class probability, and likelihood, and all these are shown here. And then we have yeah, animals. Yeah, we have size of animals, body color. Can we pet them? Yeah, so these are like different example. Let's see how these examples are being done. So all the variables are independent. That is, if the animal is a dog, that doesn't mean the size will be the medium. All the predators have an equal effect on the outcome. That is, the animal being dog doesn't mean to be, yeah. For example, like yeah, that doesn't mean to be like like it doesn't mean to be have importance for in deciding if we can pet him or no. All the features have equal importance, so these are independent events, you can say. And we are trying to apply the Naïve Bayes formula on the bound data sets. However, before that we need to be do some pre-computation on our data sets, right? So we need to find like this one for each xi in x and each y in y. All these calculations have been demonstrated like as below. Yeah, so these are the different features we have it, like for animals, for animal size and animal color. So these are the three like features, and based on that one we classify them yes or no. So let's see that how this formula is like impacting us. Yeah, so this is like a very good example here, and I hope that we can easily like solve this one. So we have like yes and no. So let's see how counts how many yes we have in the classifier. 1 2 3 4 5 6 7 yeah, 7 8 yeah. So this is 8 yes. Let me like highlight it for you so that you can understand that what I mean by 8. This is 1, this is 2, right? This is 3, this is 4, this is 5, 6, and 7, and then you have the 8, right? So this is 8 yes, we have it, and the remaining are 6 9. So no, 1, this is 2, 3, 4 and 5 and 6, right? So 6 we have no, right? So the total are how many? 8 plus 6 14. So the probability is 8 by 14, and it is 6 by 14. So we also need to probabilities P of Y, which are calculated in the below table, and the pet is animal is means no. Pet animal means no, and non-pet means yes, right? Okay. So yeah, so like okay. So in this one now let's see we have like cow, medium and black. Okay, if we use if now if we send like test data, suppose test is like this one, so let's put in that one. So for example, then in the yes in the for example in the yes in 8, how many are like this one, 3 is the first, for example, is a cow in this one. So how many cows are there in the yes? So in the yes, how many cows are there? This is the first cow. This is not the yes, this is the no cow. So this is the yes cow, and there's a third cow. Let me check where. Yeah, this is, so 3 cows are there. So say in the all yes we have 3 by 8. Okay, and then the medium size. So in the medium size, how many we have? Yes, yeah, medium. This is yes medium. Yeah, and then we have a medium here. Okay, and then we have where is the yeah, we have 2 medium. Yeah, right. So we have a 2 medium in the yes, and then we have a like black, and the black in the yes we have it like this black one. Okay, and then we have another black. Where is another black? Yes, second black, and we need a third black. Where is the third black? Yes, we have a third black, right? So this is 3 by 8. Okay, and what about this one? 8. Okay, so 8 means how many? Yes, yeah. So we already calculated 8 by 14. This is all total yes, right? And we can easily calculate. This is like for yes we have it, right? So in the next one, we will calculate the for the no as well.